In this video, we're going to use the node voltage method to find the voltage VO, which is the voltage across this 4K resistor. Now we know because we're going to be using the node voltage method, we want to identify all of our essential nodes. We know this is going to be an essential node. I'm going to call this node 1. This is another essential node. I'm going to call this node 2. And we have another essential node right here. I'm going to call this node 3. And we have a node at the bottom here, and I'm just going to take this as our reference node. Okay, so let's start to write the node voltage equations starting at node 1. We're going to assume the current is going to be leaving this node, going in these directions here. Okay, so we know we're going to be writing the node voltage equation for node 1. Okay, now we know we're going to have the voltage at node 1 divided by 12,000 to get the current flowing through that resistor. Plus, we have a current source, and this current is actually leaving from this node. So we're going to have a positive. The value of that current source is going to be 2 milliamps. So we have 2 times 10 to the negative 3. And when we look to the current in the top branch now, we're going to notice that this current, we don't know the value of this current, and we cannot find that using Ohm's law because we have a sole voltage source in this branch by itself that's going to be between two essential nodes. Now, once you've identified that, it's our job to see whether we know the voltage in one of these nodes. When we look at the voltage V1, we don't know the voltage in V1, which is the voltage in node 1. Now, when we look at node 3, we look at the branches, we don't know the voltage in node 3. Therefore, because we have a voltage source in between two essential nodes, and we don't know the value of the voltage at any of those nodes, we're going to use the supernode method. So we're just going to ignore this voltage source for now, and now write the node voltage equations at node 3. So we're going to have plus V3, and we're going to assume the current is going to move away from the node in these two directions. We're going to have V3 over 4,000, which is the current flowing through this leg. And then we're going to have plus V3 minus V2 over 6,000. And all of that is going to equal 0. Right? So really, this isn't a node voltage at node 1 anymore, but it's really a node voltage at the supernode. Right, so we just acted like this wasn't here for the moment. Okay, so now we just act like this was one big node. Now let's start to simplify this. We're going to multiply the terms by 12,000 because we know 12,000 is the LCD. When we do that, we're going to get V1 plus 24 plus 3V3 plus 2V3 minus 2V2 equals 0. So when we start to simplify this now, we're going to get V1 minus 2V2 plus 5V3, and all of that equals negative 24. Okay, I'm going to call this equation 1. So this is equation 1. V1 minus 2V2 plus 5V3 equals negative 24. Okay, now that we have this, let's also write the constraint equation one time for this supernode. So the constraint equation is going to be, we have this voltage source and we see how the polarities are written. Because node 3 is connected to the positive terminal of the voltage source, we know node 3 has a higher potential than node 1. So we're going to have V3 minus V1 equals 6. Okay, now this is going to be equation 2. I'm going to call this equation 2. Of course, we can rewrite this as negative V1 plus V3 equals positive 6. Now we have one more node, which is going to be node 2, and we're going to write a node voltage equation at node 2. So let's do that. I'm actually going to do it right here to save space. So we're going to assume the current is leaving the nodes, going in this direction, and this direction. So when we look at the current that's going to be leaving this node in this branch here, we have a current source. And because that current source is flowing towards this node, we're just going to take that current as a negative current. So we're going to have negative 2 times 10 to the negative 3, plus we have the current flowing downwards, which is going to be the voltage at node 2 divided by this 12,000 resistor to give us that current. So we have V2 minus 12,000, plus we have the current going in this direction now. So that's going to be V2 minus V3 divided by 6,000. And that's going to give us the current flowing in that branch. And all of that equals 0. Now when we simplify this, we know the LTD is going to be 12,000. So we're going to multiply each term by 12,000. That's going to give us negative 24 plus V2 plus 2V2 minus 2V3 equals 0. When we simplify this now, we're going to get 3V2 minus 2V3 equals 24. I'm going to call this equation 3. Now at this point, you can either solve for one of these unknowns. You can say V3 equals 6 plus V1. Substitute that into wherever you see V3 and solve for it that way. Or you can just set up a system of equations, and that's what I'm going to do. So because I have 3 equations and 3 unknowns, I'm just going to use a system of equations. And I'm going to use the matrix method. So I'm going to say we're going to have a 3 by 3 matrix, right? A pretty big matrix, but good thing my calculator stops at a 3 by 3. So this is perfect for me. And I think it should be perfect for you as well. For equation 1, we're going to have a positive 1, a negative 2, positive 5. Positive 1, negative 2, positive 5. And we know the unknowns are going to be V1, V2, and V3. And that equals negative 24. For equation 2, we had a negative 1. We don't have any value for V2, so we're just going to write it as 0, right? So if you want to rewrite this, we can say negative V1 plus 0 V2 plus V3 equals 6, okay? That's where we got the 0 from. Now we have a positive 1, and that equals 6. Now for equation 3, we don't have any V1, so we're just going to write it as 0. V2 is going to be positive 3, V3 is negative 2, and that equals positive 24. So we're just going to take the inverse of A and multiply it by B. Therefore, the voltage at node 1 is going to equal negative 6.43 volts. The voltage at node 2 is going to equal 7.71 volts. And the voltage at node 3 is going to equal negative 0.43 volts. So these are going to be the voltages at each node. Now the question wants us to find the voltage VO, which is going to be the same voltage at node 3. So because we know the value of the voltage at node 3, we actually know the value of the voltage VO. So we can say V3 equals VO. Therefore, VO equals negative 0.43 volts. So this is going to be our answer for this particular problem. The voltage VO equals negative 0.43 volts. If you have any questions, please leave them down below. So this was another supernode problem. And once you were able to identify it was a supernode problem, it was fairly easy after that.